All right, welcome everyone to another deep dive. Today we're taking a look at a pretty neat way to analyze electrical circuits, especially when you've got a circuit that looks, well, kind of like a plate of spaghetti.
Oh, I know that feeling.
Yeah, it can get really messy really fast, right? So we're zeroing in on this thing called the mesh current method. And from what I've gathered, it's like a secret weapon for untangling even the most complex networks. So our goal today, we're going to try and understand this technique, how it actually works, why it's so darn useful, and hopefully along the way we'll have a few of those aha moments.
Yeah, exactly. When you're staring at a circuit with tons of parts all connected together, trying to figure out all the currents and voltages directly
Yeah.
can become a real nightmare. It's like, well, like you said, a plate of spaghetti, right? You get lost in all those noodles. The mesh current method swoops in and gives you this really structured, organized way to tackle it. The real beauty of this and what makes it such a powerful tool for folks out there is that by thinking in terms of these loop currents, we kind of cleverly sidestep the need to meticulously track current at every single point where things connect. And get this, Kirchhoff's current law. It's already baked right in.
So we're shifting gears, right? We're not focusing on each individual lane of current. Instead, we're looking at the bigger picture, the bigger loops, and that helps us simplify things.
Exactly.
Now, in the material you sent over, it mentions this method as being super helpful for something called planar circuits.
Right.
What exactly does planar mean in this context?
Okay, so picture this. Imagine you're drawing the circuit on a piece of paper, right?
Right.
A planar circuit means you can draw it without any of the wires having to cross over each other. No overlapping wires.
Gotcha. So no, like, bridges or overpasses.
Exactly, no wire bridges. If you have to build a bridge, with your wires to make the circuit work on paper, then it's not planar. And at that point, we might need to pull out a different tool from our circuit analysis toolbox. But for these planar circuits, the mesh current method, it's like the go-to method. It's really systematic.
Okay, so planar, no wire bridges allowed. We've got that straight.
Yep.
Now, within these planar circuits, we've got these things called meshes.
Right.
What's the simplest way to think about a mesh? What picture should I have in my head?
Think of it as a loop, a closed path that doesn't have any other loops inside of it. It's like the smallest, most basic loop you can spot in the entire circuit.
Okay, so like thinking about a window, you've got individual panes that make up the whole window. But those individual panes, they're not divided themselves. So the mesh is like that individual pane.
Perfect. That's a great analogy.
Okay, I think I've got that. Now we bring in this idea of mesh current.
Right.
What is that, and how is it different from the current that we normally think of flowing through a wire?
Good question. So a mesh current, it's a current we kind of imagine is flowing around the edge of one of these meshes. Those little loops we talked about. It's more of a mathematical tool we use rather than a current you'd actually go and measure directly with a meter on a specific wire.
Oh, interesting. So it's more of a conceptual current, something to help us with the analysis, but not something we'd necessarily see if we poked around with a meter.
Exactly. You got it.
But then, if it's not something we can always physically measure, how does it help us understand what's actually happening in the circuit?
Well, that's where it gets really interesting. When we define these mesh currents in a consistent way for each loop, making sure we're always going in the same direction, we automatically satisfy Kirchhoff's current law every single time.
Wait, really? How does that work?
Think about it. Each mesh current, as it goes around its loop, enters and exits any node it passes through. So if you look at any node in the circuit, the total current going in will always equal the total current going out because each mesh current is like a closed loop. They balance each other out.
So it's like we're building that balance right into the way we set up the problem.
Exactly. And that's a huge time saver because it means we don't have to write out all those separate Kirchhoff's current law equations at each junction.
That sounds like it could save a ton of time and headaches, especially when things get really complex.
You got it. It streamlines the whole process. And while a single mesh current might not perfectly match the current flowing through a specific branch or wire, the actual current in any wire will be some combination of the mesh currents passing through it. It could be the sum or the difference, depending on how we define those mesh currents.
Okay, so it's like instead of tracking each individual car on the road, we're analyzing the overall traffic flow on these interconnected highways.
That's a great way to put it.
Okay, I think I'm starting to see the logic here. So mesh current method, it's like shifting our perspective from the micro to the macro. We're thinking about the overall flow within interconnected loops instead of getting bogged down in every single individual detail.
You got it.
Now, how does this mesh current method relate to the more traditional way of analyzing circuits, the one that uses branch currents? It seems like a pretty big shift in thinking.
Yeah, it is a bit of a shift. So with the branch current method, you'd assign an unknown current to every single wire in the circuit.
Oh, wow. That sounds like a lot to keep track of.
It can be, especially in big circuits. Then you'd apply Kirchhoff's current law at all the nodes, where the wires connect, and Kirchhoff's voltage law around all the loops to get a whole bunch of
And
equations.
that's where the spaghetti monster comes in, right?
Right. You end up with this massive system of equations, and it can get really messy to solve. Now, the mesh current method comes in and says, hey, let's simplify things. Instead of starting with all those branch currents and then trying to relate them with KCL, we start by defining a smaller set of mesh currents. And these mesh currents, remember, they already satisfy KCL built in.
Right. We talked about that. So we're already a step ahead.
Exactly. So we've essentially traded a potentially huge and complicated system of equations for a much smaller, more manageable set of equations. It's like, instead of trying to track every single car in a city, we're focusing on the major traffic flows on the highways.
Ah, that's a great analogy. So
Mhm.
less chaos, more order. Okay, so we've defined these mesh currents. We're already satisfying KCL. What's the next move? How do we actually start solving the circuit?
Okay, so now we shift our focus to Kirchhoff's voltage law. We're going to apply KVL around each mesh in the circuit. It's like taking a virtual tour around each loop, making note of all the voltage drops across the components and any voltage rises we get from sources within that loop. The key here is that we're going to write those voltage drops directly in terms of our defined mesh currents using Ohm's law. You remember good old V equals IR?
Oh, yeah. V equals IR. That's like the bedrock of circuit analysis.
It is. So if a resistor is part of just one mesh and there's a current flowing through it, the voltage drop across it is simply the resistance times that mesh current. Easy peasy.
Sounds straightforward enough.
Yeah.
But what happens when a resistor is shared between two meshes? That's got to complicate things a bit, right?
Absolutely. That's a great question. When a component, let's say a resistor, is part of two meshes, it means we've got two different mesh currents potentially flowing through it. The actual current through that resistor is the combination of those two mesh currents. Usually it's the difference between them, but it depends on the direction we assign to those mesh currents.
Okay, I see. So it's like two currents kind of merging or battling it out in that shared segment.
Exactly. So when you apply KVL around one of those meshes, the voltage drop across that shared resistor, it's going to depend on both mesh currents. You got to factor both of them in.
Okay, makes sense. We're taking both loops into account.
Right.
So we go through each mesh, apply KVL, write all the voltage drops in terms of our mesh currents. What do we end up with after all that?
We end up with a system of equations all nice and neatly arranged. The number of equations will be the same as the number of those independent meshes we identified earlier, and the unknowns in these equations are those mesh currents we've been working with.
So it's like a puzzle, and we have all the pieces, and now we just got to put them together.
That's a great way to put it. It's a puzzle. And the pieces are those mesh currents. So you solve that system of equations, use your algebra skills, and you get the values for all those mesh currents.
All right, so we've got the mesh currents figured out. Now what?
Well, now the fun begins. Now you can go back and calculate the actual current flowing through any branch in the circuit. You just see which mesh currents contribute to that branch, add them up or subtract them as needed, and voila, you've got your branch current.
And from those branch currents, we can figure out all sorts of other things, right? Like the voltage drops across specific components, the power being supplied or absorbed by different parts of the circuit, even the power coming from the sources.
Exactly. It's like you've unlocked the secrets of the circuit. You know all the currents. You can figure out all the voltages, all the power, everything.
Awesome. Okay,
Yeah.
that's the basic idea, and it seems pretty straightforward. But you mentioned earlier that things can get a bit more complex when we have these things called dependent sources in our circuits. What exactly are those, and how do they throw a wrench in our mesh current method?
All right, so dependent sources, they're kind of like tricksters. They're circuit elements, but their output, which could be either a voltage or a current, depends on something else happening somewhere else in the circuit. Imagine a thermostat controlling a heater, right? The heater's output, the heat, depends on the temperature in the room.
Okay, so the dependent source is like the heater, and its output depends on some other variable in the circuit, like the temperature in the room.
Perfect analogy. That means these sources, they're not constant. They change based on what's happening in another part of the circuit. So it's like a moving target.
Ah, so that's why they make things trickier. Now, how do we handle these dependent sources when we're using the mesh current method? Do we just throw our hands up in the air and say, This is too complicated?
No, no, we don't give up that easily. The basic approach stays the same. We still define our mesh currents. We still apply Kirchhoff's voltage law around each mesh, but there's a little
There's
twist.
always a twist.
Right. So when you have a dependent source, the equation you write for the mesh containing that source, or even a mesh that influences that source, it's going to involve the controlling variable of that dependent source. That's the other current or voltage that's calling the shots.
Okay, and that controlling variable, we need to express that in terms of our mesh currents as well, right? We can't just leave it hanging out there as some separate unknown thing.
You got it. You're going to need to write an additional equation, and we usually call this a constraint equation. This equation links the dependent source's controlling variable to those mesh currents we've been working with. It's like translating the dependent source's language into the language of mesh currents.
So it's like we've got our regular mesh current equations from KVL, and then we've got these bonus equations that tell us how the dependent sources are being controlled, all in terms of our mesh currents.
Exactly. You combine these constraint equations with your mesh current equations, and now you've got a bigger system of equations that you can solve all together to find all those unknown mesh currents.
All right, so let's say we've got a voltage-controlled current source where the current it pumps out depends on the voltage across a particular resistor.
Okay, I'm following.
We'd write our KVL equations like usual, but then we'd also need an extra equation that basically says, hey, that voltage across the resistor, it's equal to this combination of our mesh currents. And we'd use Ohm's law to connect those dots.
Perfect example. You're essentially saying to the dependent source, hey, we're speaking mesh currents here, so you got to play by our rules. You're bringing everything into the same framework.
Okay, so we've added a step, but it seems manageable.
Mm-hmm.
Define the meshes, define the mesh currents, write the KVL equations, and then for each dependent source, figure out its controlling variable and write a constraint equation that links it to those mesh currents. Then we solve the whole shebang.
You got it. It's systematic. And once you have those mesh currents, you can still find all the other goodies you need, like branch currents, voltages, power, everything.
All right, so we've covered the basics. We've tackled dependent sources. Now let's dive into a special case that the material you sent over highlights. The supermesh. What is this supermesh all about, and why does it sound so, well, super?
Okay, so the supermesh idea comes into play when you've got an independent current source that's sitting in a branch shared by two meshes. You know, like those shared resistors we talked about. But this time it's a current source causing the trouble.
Okay, so two meshes sharing a current source. What's the problem there? Why do we need a special technique?
If you try to apply KVL, our good friend Kirchhoff's voltage law, around a mesh containing an independent current source, you run into a snag. See, you know the current flowing through that source, it's given, but you don't immediately know the voltage across it. That voltage becomes another unknown in your KVL equation, and our standard mesh current approach isn't really designed to handle that directly.
So it's like we've got a known current, but an unknown voltage in the loop. That does seem like a problem. So how does the supermesh come to the rescue? What's its superpower?
The supermesh is a really clever way to basically avoid dealing with that unknown voltage across the current source altogether. We sidestep it.
Okay, I'm really curious now. How do we actually create this supermesh? What's the magic trick?
Imagine this. You temporarily take that independent current source out of the circuit. You just pretend it's not there for a moment.
Okay, so we're just ignoring it. That seems a bit bold.
We're not completely ignoring it, but we're setting it aside for a moment. And when you do that, the two meshes that were sharing that current source, they merge into one big happy loop. And that, my friend, is your supermesh.
So we're combining two loops into one mega loop, bypassing that troublesome current source in the middle. But how does that help us with KVL?
Now, you apply KVL around this entire supermesh just like you would for any regular mesh. But the key here is that when you add up all the voltage drops and rises around this bigger loop, you write all those voltages in terms of the original mesh currents that were flowing through those two merged meshes. Because you mentally remove the current source, its mystery voltage doesn't appear in your KVL equation.
That's pretty slick. We've sidestepped the problem. So we get one KVL equation for this supermesh. But we can't just forget about that current source completely, can we? It'd have to have some influence on the circuit.
You're absolutely right. That current source, even though we temporarily banished it from our KVL equation, still dictates the relationship between those two mesh currents that were flowing through its branch. The difference between those two mesh currents, or sometimes the sum depending on how we define their directions, has to be equal to the value of the independent current source. That's our constraint equation.
Ah, so the current source might be gone from the KVL equation, but it's still whispering in our ear, telling us how those mesh currents are related.
Exactly. It's like the ghost of the current source, still haunting our calculations.
So you've got one KVL equation from the supermesh and one constraint equation from the ghost of the current source. Two equations, two unknowns we can solve for those mesh currents.
Bingo. You've got it. For every independent current source that's causing trouble between two meshes, you form a supermesh, write a KVL equation for it, and let the current source give you that extra constraint equation to link the mesh currents.
That's a pretty elegant solution.
Yeah.
So now, dib question. Can we use this supermesh trickery when we have a dependent current source hanging out between two meshes?
You bet we can. And the approach is very similar. If you have a dependent current source making things complicated between two meshes, you do the same thing. Mentally remove that current source, form your supermesh, and apply KVL around that big loop, writing all your voltages in terms of those trusty mesh currents.
And just like before, we'll need a constraint equation, but this time it's going to involve the controlling variable of that dependent current source, right? That other current or voltage that's pulling the strings.
Exactly. Your constraint equation is going to describe how that dependent current source is behaving. And it'll be written in terms of those mesh currents we've been working with. So you'll have one KVL equation from the supermesh and one constraint equation from the dependent current source. Solve those together, and you've got your mesh currents.
So it's the same basic idea, whether it's an independent or a dependent current source causing mischief. We create a supermesh, write a KVL equation, get a constraint equation from the current source, and we're in business.
Precisely. The supermesh is a powerful tool. It lets us analyze circuits with current sources without getting bogged down in unknown voltages. It's like a secret passageway that lets us bypass the obstacles.
This has been a fascinating journey into the world of mesh currents. We've gone from the basic concept to handling those tricky dependent sources, and we've even learned how to deal with current sources by forming supermeshes.
It's amazing how much you can simplify complex circuits just by thinking in terms of loop currents and applying KVL strategically.
And for our listeners out there, if you're ever wondering whether to use the mesh current method or a different technique like the node voltage method, take a look at the circuit. How many meshes are there? How many nodes? That can give you a hint about which method might be more efficient.
Both methods are powerful, and knowing both gives you more options. It's like having different tools in your toolkit ready for whatever circuit challenges come your way.
Thank you so much for joining us on this deep dive. Hopefully it sheds some light on the beauty and power of the mesh current method. And who knows, maybe it's even sparked a little curiosity to explore the world of circuit analysis even further. Until next time.